All right, we're back. We now turn to page 2 of this packet. And no, 3. Page 3 of this packet. Page 3 of this packet is the seemingly very innocent statement that every line has at least 2 points on it. Claim every line has at least 2 points. Okay, this sounds like very obvious, but actually is like quite difficult to prove. Well, not difficult, but it's a little, it's very abstract, and Gossett just like skips this entirely. Okay, ready? Say ready.
Ready.
Woo! Okay, this proof is due to Dennison. Take an arbitrary line L. Okay. Well, I'm going to prove to you that this line must have 2 points by contradiction. So, suppose L has just 1 point. Suppose L has just 1 point on P. Alright, so my line L looks like this. There's a single point P on this line. This is not possible because every 2 lines meet. Since every 2 lines meet, and there's only 1 point on line L, then every other line that meets L must meet L at P.
Wait, this is like tangentially related. I was trying to do the proof last night, and
This proof?
No.
That proof that we just did?
Yeah.
Yeah?
And I was like running into issues with, so every line intersects every other line, right?
Yeah.
Doesn't that just like spiral out of control with points and stuff?
No. Can I get to that in like 5 minutes?
Yeah.
Okay, cool. Okay, that's like the very next thing we're gonna do. Okay, so okay, here we are. So here's the line that has 1 point on it. All right. So since every pair of lines meets at a point, and there's only 1 point on L, and there's only 1 point on L, then every line meets L at point P. Who is with me? All right, I heard one tiny audible noise. Good. Woo. Well, notice I'm being very kind of abstract at this moment because I don't know what this line L is. But here's what I'm now going to say. What do I know? What kind of lines do I know are always there, man? Say the core 4. The core 4. Yes, there are always a core 4 lines. That's what FTP3 prime says, that there exists 4 distinct lines, no 3 of which contain a common point. So now we go, but by FTP3 prime, we have 4 lines. We have 4 lines, and those 4 lines are L1, L2, L3, and L4, let's say. No 3 of which meet at a point. All right, now here's where it gets a little bit weird, because I don't know whether line L is one of those lines or not, but it doesn't matter, because already, if L is not L1, L2, L3, or L4, then I have all of L1, L2, L3, and L4 meeting L at P. Because I know I have those 4 core distinct lines, and I know they must intersect every other line, and there's only 1 point on L, so they all go through P. If L is one of those points, if L is one of those lines, are you guys following this? It's so abstract. If L is one of those 4 lines, well then fine. The other 3 each intersect L. And then the other 3 can only intersect L at L's only point, which is P. And so either way, since every line passes through P, then we have either 3 or possibly even 4 of those core 4 lines meeting at P. Who's following me? We have either 3 of those lines if L is one of them, or 4 of those lines if L is not one of them, or 4 of L1, L2, L3, and L4 meeting at P. And that is exactly what can't happen, because the core 4 lines guaranteed by FPP3 prime just like don't meet at a common point, yet they're all meeting at P. Cool? All right, this proves that every line has 2 points on it. All right, and yeah, while that might seem obvious, it's actually quite like, I don't know, it takes a little bit of creativity to come up with a proof like that. Yes?
So like, this is kind of like esoteric, but would you have to prove that, how would you say that, like, what if L had like no points?
Oh yeah, someone even asked this last year. Oh god. All right, putting me on the spot. Could a line have like no points on it? No, because, well, you tell me.
Because by...
Suppose you had a line L with no points on it.
And then you can't make another line.
Yeah, but then there's the core, there are the core 4 lines, L1, L2, L3, and L4. And those L must intersect by FPP2. No, FPP2 says every 2 lines meet. And so like, look, perhaps L is one of the L2, L1, L2, L3, L4, but it can only be at most one of them. So there's still the other 3 lines to contend with. And L must intersect all those lines, and so it must intersect them somewhere. Yeah. So it's, do you sort of feel that like the F, do you want me to say that again slower?
No, I understand it, like, but would you have to write it down?
Yeah, probably. But it's not on the packet. Maybe it should be later. But yeah, notice that I tried to talk about this a lot last class, but maybe you weren't ready for this conversation yet at the time, which is that like FPP1 and FPP2 like sort of govern the geometry in a sense by saying that there's a line through every 2 points and there's a point where every 2 lines meet. But it's FPP3 which is sort of saying that your geometry is not trivial. Because you could, if you just had a model with no points and no lines, that would satisfy FPP1 and 2. Or if you had just like one single line with like 2 points on it, that would also satisfy L1 and L2. FPP1 and FPP2. But we don't want that. Okay, good. All right, so in fact, every line must have at least 3 points on it, which I think is the hardest proof I've ever done inside Blair High School, which we're going to do in about 5 minutes. So first, a break. Let's see what one model looks like. We actually did this already last class, but I didn't make a big deal for the time. Or maybe I did, I don't know. It's called the Fano Plane. And now that we've eliminated the idea of there being like, since every line must have at least 2 points, then let's just kind of start drawing and see what we see. Well, we sort of did this last class, right? If there must be this core 4 of points and lines, and one benefit of having done this thing last class in excruciating detail is that we can now start proofs like already at that point and just kind of call it done. And so, I don't want to confuse people with a new orientation, but what we said was like, yo, you have this line L1, L2, well, the way we actually did it was to say that there's these 4 core points, P1 through P4. So P1, P2, P3, and P4. And perhaps I should use, this is a good time for colors. Yeah. And so, good. And then what we said is, okay, well, there must be a line through P1 and P2, let's call it L1. There must be a line through P3 and P4, let's call it L2. Those lines are parallel or something, but we actually know that no lines are parallel in this in a projected geometry. Okay, so more on that in a second. then we have also a line through P1 and P3. This is L3, and a line through P2 and P4. That's L4. And then we have this other line, the line through P2 and P3, which I called L5. And now, depending on your artistic sensibilities, you could either draw it crossed, or if you prefer to think of them as parallel, you could do it like this, having kind of slope 1 or something like that, and then we'll call this L6. The lines on the paper are not part of what's really going on. They're just pictures that help us think. Okay, so these are 6 lines, and note that this is the picture we had on the board on Friday. It is not a model of the finite projective plane axioms, of course, because it violates some of the axioms. What axiom does it violate?
There's lines that don't meet.
Yeah, every 2 lines must meet at a point. And so if every 2 lines must meet at a point, the ones that are sort of violating the axioms at this moment are the ones that have drawn to be sort of parallel, right? So I think of this, and this is why I spent like 25 minutes last class talking about this weird unit that like some people did 10 years ago, because I do think it's helpful to think of like a finite Euclidean geometry before you go into a finite projective geometry. In a finite Euclidean geometry, this would be a model. And everything would be great. This would be called the 4-point model with 6 lines, not if you're like, yeah, let's hear last class, I know what you're talking about. But in a projective geometry, points are always meeting. So L1 and L2 do meet. They meet at like the point at infinity with respect to parallel lines L1 and L2. I'm going to continue calling them parallel lines, even though they're just clearly not parallel, because they meet, but they're parallel-ish. And they meet at this point. Let's call this point infinity 1. It's the point at infinity with respect to the first equivalence class of parallel lines L1 and L2. And then also, there's this point at infinity, which I'll call infinity 2, where, in order to sort of patch up the model and make L3 and L4 intersect somewhere, they intersect there. And then there is a point where these 2 lines meet, and I'll call that infinity 3. And now I claim that this just is a model. And it suffices to just check the axioms sort of exhaustively and see if indeed this model satisfies the axioms.
Does it? Right?
I think it does.
Infinity 1 and
Oh,
infinity
no,
2
I screwed up. He's right. There's a problem. What's the problem?
Infinity 1 and infinity 2 aren't like a common
Yes,
line.
I just, right. I almost had it, but then I didn't have it. Which is that now that I've created these 3 new points, because every pair of lines must meet at a point, I now need there to be a line through these points. And in fact, we can now connect them, and there is this line which goes through the 3 infinity points, which we might as well call it L infinity or something like that. Or you could just call it L 7. Which is the line through all the points at infinity. It's sort of like the circle at infinity. Who's with me? Woo! Well, Fano is maybe like Hungarian or something. I believe it's pronounced Fano. This is called the Fano Plane, and the Fano Plane is the minimum. I hope you agree that this is like the minimum model. Like you can't get by with fewer points than this because you need to. Yes.
Couldn't you make all three sets of parallel lines meet at the same infinity point?
I don't think you could, because if you did that, you would now have, for example...
Oh, because core 4 lines would meet at...
Now you would have 3 of the core 4 meeting at a point, and that's what you can't do. Yeah, exactly. I probably should have mentioned that, right? That's why these infinity points needed to be different infinity points, because if L1 and L2 are going to meet at infinity 1, then L3 and L4 can't go through infinity 1 because they're part of the core 4. Okay, wait, you had a question?
Yeah, how is it not just like cheating to say, oh, these points are off at infinity, don't worry about it? Also,
Well,
why do
infinity
they
is a kind of a way of thinking about it. It's still just 7 points.
Okay, but
If you want me to call these, I can rename these
No,
P 5, 6, 7.
but why do they have to be parallel? Why? Like,
Say that to me one more time.
why do any of the lines have to be parallel here?
Okay, wait. So none of the lines are parallel because there are no parallel lines in a projective geometry. One thing I could do right now is just to maybe dispel some confusion. Let's just never mind all this infinity mumbo jumbo, and let's just call it what it is. This is just a point, man. What is this point? Let's call it P5. What is this point? Let's call it P6. What is this point? Let's call it P7. And let's just call this line L7. Maybe that's actually better because we see that we have precisely 7 points and precisely 7 lines, which is sort of emphasizes the duality. And now my model, the picture is good for us because we're human beings, but the picture is like not really what's going on. What's really going on is that there's a line L1, which consists of a finite set of points. Like a line is uniquely determined by the points that are on it. What points are on L1? P1, P2, and P5. And what is on L2? P3, P4, P5, etc. Can I not write all these out? So Evan, the idea here is like that it's like the list of the points and the list of the lines and the list of precisely what points are on what line. That is really the model. This is just like a visual representation of the model. Does that kind of answer your question? Okay. So in fact, no lines are parallel. But I like to think of it sort of still as being a geometry. Okay, this is not the way the Fano plane is usually depicted. The Fano plane is usually depicted kind of artistically in a sort of a different way, which I used to not like, but now maybe I like more. I don't know. It looks like this. If you turn to page something, page 430, you will see that there you can depict the Fano plane in a kind of a triangle, and then there's like a circle. Shoot. That's the worst circle I've ever drawn inside a triangle. And then you got this, this,
Oh my god.
this.
Yeah.
What's going on?
Oh, yeah. I have many other ones though.
Why did something get quiet? What happened?
The
Oh, the air conditioning stopped.
Man,
We're all doomed.
Yeah.
I mean, in the big picture, yes. All right, good. So note there are 7 points labeled A, B, C, D, E, F, G, and there are 7 lines. And like basically, this is just kind of like the stylized version. So here's L1 and L2. Here's L3 and L4. Here's L5 and L6. And then L7 is, no, I guess this is L7. L4 is maybe the circle? Can't tell, can you? I think L4 is the circle.
L4 is the more Cedric guys.
Okay, so, and maybe I'll do like a little, maybe I'll do this. Okay, so what the hell is going on here? Well, again, every 2 points is on a line. Confirm that through every 2 points is a line. This is the cool way of drawing the Fano plane. Through every 2, oh my god, what time is it? Holy crap.
203.
Yikes. Okay, good, the Fano plane. I also have, should we say what's going on here? Let's see. So L1 and L2 are parallel lines. If we want to merge this with our understanding, right? L1 and L2 are parallel. They meet at the point at infinity. Thus, A is one of my points at infinity. Who's with me? L3 and L4 are also quote-unquote parallel, but meet at their point at infinity, which is F. Yeah, this is right. And L5 and L6 are quote-unquote parallel, but meet at their point at infinity, which is G. And thus, the line L7 is like the line through infinity. It's like a lot going on here. I'm just going to throw one more thing into the mix, which is make sure this makes it into the camera. This is a 3D printed piece of metal, which is like a 3D representation of the Fano Plane. Okay, so these are meant to be, should we all like crowd around, or it took me like hours before I even understood this, and then I haven't bothered looking at it again. Can you grab the camera and we're gonna go handheld for like a couple minutes? Do you know how to do that? No, you can like unhook it.
Okay. Hold the tripod.
Yeah, you just like, no, there's like a, it's like a hook. It's like a, who knows like things. Yeah, that one, yep.
Yeah.
Yep, keep going. Okay, yeah, good. Okay, do I remember this? No. But I will in a second. It's pretty though, right?
Yeah.
This is a single Fano plane. First note that there are 7 points. Fact.
Yeah.
So, and every point where 2 lines meet is like a point at infinity. No. I don't really know what's going on. But I will in a minute. Maybe.
There's not an intersection with less than 3 lines.
Yeah. Which is true in the model too, right?
Yeah.
Every point meets at 3.
You can like
I'm gonna
hold
set
it
this
up
down,
with paper.
and we're gonna play with this.
There is.
I want to get one more thing
Pull it
done
out.
today, so let's get started. Take it back. Let's go now. Let's go unhandled.
L7 and
The
L4.
tripod's the magnet.
Aren't there like 2 intersections?
Magnet is
L7 and L4.
You know, like
No.
magnets is such a cool name.
That's not a real intersection.
Magnets.
Oh yeah, you missed that conversation. All right, good. We have 24 minutes. We are now going to prove what I consider to be the most difficult. No, we're going to go to this board. The most difficult proof I have ever attempted. It is difficult not because of like the number of steps or like the algebra, but it's difficult because of like the abstraction. It's so abstract. To avoid terrible casework, what you need to do is just like not know what the hell is going on at any given point. Are you ready?
Yeah. Always.
All right, let us begin. Do we have time for this? Sure we do. All right. I'm going to prove to you that every line has at least 3 points. I've reserved 2 whole freaking pages in the packet for this. So get yourself like an open face sandwich, and let's go. All right. Theorem. You know what I'm talking about. Theorem. Every line contains at least 3 points. And when I eventually have my coffee date with Gossip, we're gonna have a long conversation about his bogus proof of this, because it's just embarrassingly impossible to follow and just plain old wrong. Ready? I wasted 10 hours of my life trying to make some sense of it before I decided it's just garbage. Okay. Or maybe I just don't get it. Alright, here we go. How are we going to do this? By contradiction. Suppose suppose line L has exactly 2 points. Call them P1 and P2. Call them P1 and P2. So, here is my line L, here is my point P1, here is my point P2. This is just the picture. The actual proof is happening here, which is that P1 is on L, P2 is on L, and also P1 is not P2. We got a recording, right? Double check. Alright, why is this impossible? Well,
That's gonna be immortalized.
by FPP3 prime, we have 4 distinct lines. And those lines are L1, L2, L3, and L4, the core 4 lines. And what do we know? We know that no 3 of them contain a common point. Okay, well, the first case to consider is the case that L is one of those core four. Pause for comprehension. Okay, yeah. Case 1. L is one of these core four lines, L1, L2, L3, and L4. Well, if L is one of them, it doesn't matter which, man. So, without loss of generality, let L be L1. No, let L be L4. Okay, so now I know a couple of things. I know that the four core lines are all distinct. That's previously proven. So I will now say that since L is not L1, L is not L2, and L is not L3, I invoke FPP2 to say that there are points of intersection. So by FPP2, L intersects each of these. L intersects each of these lines. In other words, there are points of intersection between L and L1, L2, L3. Okay, I will name those points respectively Q1, Q2, and Q3. In other words, let L intersect L1 be called Q1, let L intersect L2 be called Q2, and let L intersect L3 be called Q3. Alright, well, does anyone see a problem? My line L.
There's no L.
I have only 2 points on L. But I have these core four lines, no three of which contain a common point. And right now I'm in the case in which L is one of those core four. That it's L4 without loss of generality. But then I know that L must meet L1, L2, and L3. Well, what are the possibilities? They could all go through L1, right? Is that allowed? Certainly not, because L1, L2, and L3 are not allowed to all meet at a point. Could 2 of them go through P1 and 1 through P2?
No.
Also not allowed, because if 2 of them went through P1, but L is also L4 in this case. So that's not possible either. Okay, so in fact what I want to do is now invoke the pigeonhole principle. Yeah. By the pigeonhole principle, what can we say? This is a little silly. By the pigeonhole principle, L1, L2, and L3 meet L at only 2 places. Those 2 places being P1 and P2. But there are 3 points of intersection. So 2 of Q1, Q2, Q3 are the same. Okay. I got 3 lines meeting L, but there are only 2 places on L for those 3 lines to meet. So of those 3 points of intersection, 2 of them must be the same. Remember, there must be 2 lines. 2 of those lines, L1, L2, and L3, must meet L at the same P1 or P2. Okay, so without loss of generality, if of those 2 Q's, what's kind of crazy here is I'm saying, I'm handling all the cases simultaneously. The cases in which 3 of them go through P1, or whatever. It's so without loss of generality, let Q1 equal Q2, which is just another way of saying let L1 and L2 meet L in the same place. Not saying whether it's P1 or P2, because that's just distracting. Who's with me? Okay, Good. And so what do I know? I know that Q1 is on L. I know that Q1 is on L1. It's the definition of Q1. And I also know that Q1 is on L2 because Q1 equals Q2. And Q2 is on L2 by definition. Why is this impossible? Well, note that, do not forget, that L is really L4. So we also have Q1 on L4. Contradiction. I cannot have Q1 on L1, Q1 on L2, and Q1 on L4. This is 3 of the lines L1, L2, L3, and L4 meeting at a point, and that can't happen. Contradiction with FPP3 prime. Question?
Q1 is an element of L1.
Okay. This was the chill part. Okay? What makes it hard is just that it was so abstract. But this is like the only way to do it without descending into like a nightmare of cases. Alright, much harder is case 2. Alright, case 2. Case 2 is that the line L is not one of the core 4 lines. So, let L be not one of lines L1, L2, L3, and L4. Still, this is impossible. Okay. Well, if L is not among these, then what do I know? Well, I do know that L must meet each of these lines. Yeah? So by FPP2, we have points of intersection between L and each of these lines. So I know that L intersects L1. Let's call that point Q1. I know that L intersects L2. Let's call that point Q2. L intersects L3. Let's call that point Q3. And L intersects L4. Let's call that point Q4. Okay. Good. Well, next.
Make sure I do this correctly.
Yeah, good. Okay, next.
Camera in?
What's up?
Probably plug the camera in.
I think it's okay. I think I checked the battery time. I think it's alright. Unless is it blinking? No, I think it's good. Okay, well, what do I know about